but we kind of want a circuitous way to get there, a long way to get there. So instead, I'm going to do a different route, which involves not finding the tension.
Instead of finding the force and method directly by using coordinate system, we can use the energy system.
I don't know, let me do this one. So the way I'm going to do it is by defining the system differently. The method 2 is, now I'm going to consider the entire thing my system. Except the motor. So this is my system. Okay, that's kind of a bad picture, sorry. So this is the elevator. This is the counterweight. And I'm going to call the elevator and the counterweight and the pulley, the rope and everything. That's your system. So that means now when I write down the kinetic energy, I got to include the kinetic energy of both of those things. Both the elevator and the counterweight. And I got to include the potential energy of both those things too. So if I write down this formula, again, the kinetic is 0 because it's going to start and end at rest. But the change in potential energy this time, I got to write down both of them. Okay? So let me write down U2F minus U2I. That's the final potential of the second mass. And this is the final and initial of the first mass equals, sorry, this is the work applied, equals the work of the motor. Because the only work I'm doing in the system now is whatever the motor's doing. That's the only thing I need to include in my system. And I was smart about it, because I wanted to find that, so I included my system. That way, that's the whole right side of the equation is whatever this stuff is. Okay. Now look what happens on the left-hand side. If you're starting from, here's your 0 point, you can put two different zeros for two different methods. For this guy, his initial gravitation was 0, and his final is mg times the distance. So for the first mass, the initial is 0, and this one is m1g times the distance. For the height. And then for the second guy, he's starting, let's say he starts at 0, he goes down m2 times g times d. He goes down a distance of d. So his initial is also 0, but his final is below 0. So his final is actually negative, which gives me minus m2 gd equals the work of the motor. And if you just combine these terms here, you're going to have, sorry, h. You're going to have gh times m1 minus m2 equals the work of the motor. Okay, so this formula is the same as what I got in the first one. But the steps required to do it, there's only really 2 steps, and they're very straightforward. It's just potential energy of gravity, very simple. And it gives you how much work the motor did. It has to do whatever the difference is in the weight. So that kind of makes sense. If they're very equal in weight, they don't have to do much work because it's just going to push itself down. But if they're very different in weight, and this counterweight isn't weighing enough, you've got to do a lot more work to pull the other one up.
Why do you not consider kinetic energy again?
It says it starts and ends at rest. Okay? So again, the point of this exercise was to show you that if you're going to do these kind of things, you need to kind of at least have some, you need to at least know what you're defining as your system. Even if you do it in your head, it's fine, but you got to know what your system is. If you're going to consider this whole thing as your system, maybe draw it in your paper and say, well, these things are all inside my system, so I need to know what every single one kinetic energy is and every single one potential energy is. And then everything outside that's connected is going to be my external work or external forces. And the inside, there's that tension in that cable, but we didn't have to find it. We bypassed that entire part and still got the right answer because all that did was it changed the form of energy, but it doesn't move it in or out of the system. That's why energy is such a nice concept, is you don't have to worry kind of how it's transmuted. All you need is a formula for 2 different types, and you can find out what they are. Yeah.
So is it better to use energy than using forces?
Yeah, is it better to use energy than forces? That's why we teach it to you second.
Okay.
Because it's easier.
Okay.
Otherwise, if we taught you energy first, you would never use forces.
All right.
Say that again?
With these up to potential energy system to measure the change of potential energy of natural and
What do you mean 2 different energy systems?
because the origin of natural and the origin of natural.
Oh, yeah. You can do that.
So it doesn't matter.
It doesn't matter where you use it, you can send it to All right. Let me do another one homework. Let me do
Number 7. No, number 7. In fact, I'm gonna text you before I leave.
maybe just write number 9. This is the problem with those two blocks on RAM. This problem has come up like a billion times, so it's obviously a physicist like the second problem. I'm going to keep everything as variables because, again, I want you guys to get the habit of using variables, not numbers. So the problem says there's a 50 kilogram block and a 100 kilogram block. They're connected by a string over this inclined plane thing. And there's friction in the plane, so there's some friction with forces. The whole thing is moving like this. So it actually tells you which direction we move, which is nice. And it wants you to find the change in kinetic energy of the 50 kilogram block. And so the question is, what is the change in kinetic energy of 1? The first block. And the total distance, it gives you the distance it moved as well. So you know d equals 20, m1 equals 50, m2 equals 100, theta equals 37, coefficient of kinetic friction is 0.25.
If you have to calculate the change in kinetic energy, then would you need to know the initial velocity, essentially? I mean, if it's
No,
just-
because it's asking you change. So it's just asking you the difference between the final and the...
Initially, it's not moving. Or is it moving? Like, that's why I never understood that.
You don't know. In this case, it doesn't matter. It's just asking for change. So it could be moving before, but the change is still the same. All right, so basically what's happening is this thing is pulling another block up and it's accelerating. So its speed has to be increasing, which is why its kinetic energy changes. Also, there's some energy coming out of that system because of frictional force. So it's slowing it. There's one thing kind of speeding it up, but the friction is also kind of slowing it down. So there's kind of two forces at play. Now this thing has 2 blocks in it. So what I want to do is first decide what should I put in my system. Should I make both of the blocks in my system, or just one of them? Does anybody want to vouch for one of those choices? Because they're both viable ways to do it. Yeah.
What I did, I made them separate. I did the vertical one with its own thing, and I ended up solving for A to try to ultimately get that.
Okay, so he chose 2 different systems, but you had to solve for A.
Yeah,
Okay.
so more kinematics instead of energy.
Okay, so you do have to solve for A, so you might have to use kinematics or Newton's second law. If I make the whole thing my system, one thing that's nice if I make the whole thing my system, if I make this whole thing my system, like both the blocks and the pulley, is that the nice thing about that is I don't need to worry about what the tension force is because it's within the system. So it doesn't transmit anything in or out. So it's going to be in the left-hand side of the equation. I don't need to worry about that. But if I do make the whole thing my system, let me ask you this. There's one extra force in that system, which I haven't really considered, which is the normal force. The normal force is not a conservative force, per se, I guess. And it's also, I'm not going to include it in my system. I'm just including the 2 blocks. So do I need to include that amount of work that it is in this as well? Is it in the 5?
No, it doesn't do anything.
See that again?
No, this is straight perpendicular to the surface.
Okay, so what if it's going perpendicular?
Does no work.
Yeah, the normal force is, in this case, it's normal, it's perpendicular to how it moves. So if it's moving like this, the force goes up, the theta between those is 90, so the force is 0. The work is 0, sorry. So the normal force never does any work. All it does is change direction. It won't speed up anything or slow it down. So we don't worry about that. So what I'm going to do, I'm going to make this whole thing my system. Which means I need to write down all the kinetic energies and potential energies for both. Now, in this case, I have no applied forces in this because I made the whole thing my system. so the tension is within the system. It's not applied. I do have friction. Kinetic energies is what it's asking for, so I need to keep that. And it's obviously going to be a change in potential energies. Okay? So let me write this delta K1. Delta T1, delta T2. I might break this up into two different blocks, the change in neutral, plus UF1 minus UI1 plus UF2 minus UI2. Okay, so what this is saying is that the final potential of the first block, the initial potential of the first block, final of the second, initial of the second. I've got to consider both blocks, both at the beginning and at the end. And you can set the 0 point where you like for each one. You can set them separately. You can set them at different points. I also need to find the work of friction. So I do need to find the friction force as well. Which I might need to use some free body diagrams out of that. But that's something you've seen many times, so it shouldn't be too unfamiliar. Now on the left-hand side, these things I still don't know, so I keep them how they are. Okay, so for this left block, which I call block 1, it's starting here, right here, and it's moving up some distance. So I'm going to call this my 0 point, and it's moving up some distance. And you can find out how much it's moving up by just using trigonometry, because it tells you how long this. It tells you how long the horizontal distance or the diagonal distance is, and it's asking you what's the height that it changes up. So just use trig to find out what this distance is. Let me draw that for the triangle. I'll draw it over here. And this block moves up like this. And this distance is d, which you know, and this is theta, which you know. So if you want to find out the height that it moves, that's just going to be d sine theta. So its final kinetic energy is m1g times d times sine theta. Its initial is 0. Now for the second guy, it's a little easier because he's starting here, let's say, and he's going down. But he's also going down d, because if this guy moves d that way, the other guy has to move d down as well. They're connected. So that's one of the constraints of the problem. So his initial is 0. I'm going to call this a 0 point. But his final is below the 0 point, so it has to be negative. So his final is minus m2g d. Now, I'm being very careful about the negative signs, because these are the only things that can really mess it up in the types of problems. Everything else is pretty mechanical. Now the frictional force, I do need to find the frictional force. So let me just go ahead and run a free body diagram for that guy. So friction pointing downward because he's moving this way. Tension pulling up, weights pulling down. The frictional force is going to be, you're going to have to use the x components. Let me call this my x. You have to use the x components to find out what the frictional force is.
mg cosine?
Yeah, so F. Sorry. Yeah, when things are moving, your frictional force is just mu k times the normal force. And if you do the components here, you're going to get this is W1 cosine theta. I don't want to do that again, I've done it a lot of times. If you have trouble finding that, just leave it at this one. And so this will be mu k, the normal force is W1 cosine theta. If you do Newton's law in this direction, you're going to get that. So I'll plug it in there. So this is the friction force right here. And then still going to multiply with the distance.
I have a question.
Yeah.
So for the for D and that equation, the final equation, one of them is negative and the other one is positive, so they're related.
Oh, D, I'm keeping D positive. I'm already taking into account the sign.
Well, you're you're subtracting the second, yeah, that minus sign there.
Yeah.
So isn't that because you made D negative?
Yeah, sorry, yeah. But I'm not gonna plug in a negative number. Like when you plug in D, you're gonna plug in a negative number. You're gonna plug in a positive number.
But you subtracted it. Why did
Because
you
you-
subtract it? It's going down?
Because it started at 0 and its final was below 0.
Okay. So it is related to the previous usage of D then? Because that one raised, so
Yeah,
it's
yeah, yeah. So
positive?
it's the same number.
Okay.
I have a question.
Yeah.
So you said earlier that the work provided by friction is negative, right?
Right.
And then you did negative work of friction. So shouldn't it be negative and times a negative makes it positive?
When I said it's negative, this is accounting for that.
Oh,
So when you plug in F, I've already taken that account, so I'm gonna plug in all positive numbers here.
okay.
Sorry, I know it's a little confusing. All right, so let's look at this equation and figure out what we're looking for. Every step you kind of ask yourself, am I doing this in the right manner? Am I forgetting something? What am I looking for? Here you have all these numbers. You have D, W1, yeah. Theta I know, D, M, G. I don't know this. And I'm looking for this, so I need to keep that there. But I don't know delta T2. Let me write these as 1/2 M. I'll write V1 F squared minus V1 initial squared. So this is the change in kinetic energy of the first guy. Is that clear? I just took 1/2 mv squared and factored out the 1/2 m. And the second guy is the same thing. So this is this term, and this is this term. And then everything else I'm not going to write. So. Okay, again, I'm looking for this quantity. But it looks like I have a bunch of other unknown quantities. How am I going to solve for it when I don't know these velocities? I don't know V2F or V2I. How am I going to solve for it? Any ideas? How come?
Because they're connected by the same rope.
Yeah, they're connected, so they're going to have the same velocity at all times. So this is actually the same as that. So let me just call this VF. I'm going to take out the 2 and the 1. You don't need the 1 here, because they're the same. So I can actually factor this whole thing again. 1/2 M1 plus M2. What I'm doing is taking out the M1 and M2 out of both terms. You're left with this. Plus the rest of the stuff here, which is M1G D sine theta minus M2G D equals minus mu K W1 cosine theta. Are there any questions up to this point? Well, there's a lot of work here.
How come you where is it? For mass 2, how come it's just D and it's not D sine theta?
Oh, because that mass is going straight down, not in an angle.
Okay.
Any questions? Yeah. Yeah, because they're connected and the string doesn't get slack. So. All right, so now we only have one missing quantity in this thing. There's really two, but I'm going to call one thing. Because the goal is to find this. That's the goal. That's the change in kinetic energy of the first guy. So if I know this quantity, I know everything. And you're pretty much there. You just have to solve for that quantity. And you can solve for that thing and then plug that back in here to find the kinetic energy of the first one. Now, one thing that you should notice here is that because I chose my system as 2 blocks, I avoided a lot of free body diagrams. I didn't have to find the tension at any point. That's the beauty of, or it really helps if you want to keep the tension inside your system, which means your blocks is in the system and the tension is also there. So if that's included in there, you don't need to account for it at any point. All it does is it changes the energy within, but you don't have to find out what it actually is. The free body diagram stuff can be a little, it can be like a little tedious. That's why it's good to avoid it. If you can. Now, if you made your system just 1 block, you would get the same answer. So it's totally viable to do that. Right, are there any questions on this? Any other questions? Yeah.
Why can't you leave that quantity there just as delta T in the beginning?
Say that again?
Like the goal, you're trying to find the change in kinetic energy. Why can't you just leave that as delta T and then solve the whole thing at once?
Because that would be the change in kinetic energy of both the blocks. And you don't want to include the change in kinetic energy of the second block. So I had to separate them. So this second block is the same thing, but it's times n2. We'll describe it times n1. And I just want the first block to be times n1. Yeah, the problem is a little tricky. It's a lot of work, but that's pretty much how you do it. Okay, so again, you start with the same formula. You always start with this formula, and plug in what you know and don't have, and then at every step along the way, ask yourself what you're missing, and you go back and solve those formulas. Yeah.
You said when you finish it there, you're treating like that whole thing like pretty much just like one term?
Yeah, treat it like X.
Okay.
Okay, the last thing I want to talk about in the last 10-15 minutes is potential energy functions. We didn't say too much about this. This is something that's going to come up again in 2B. Because there's a big connection between potential energy functions when we talk about voltages and electric fields. Says the relationship between potential energy and force. Now, I've written this equation down earlier, which was that the force, a conservative force, equals the derivative of some potential function. If you can find that antiderivative, things are a lot easier. And the question a lot of students had in class is, why is there a negative there? And it's a definition, so it's just kind of like we can define things however we want, and as long as we're consistent with that, nothing is wrong. But there's a reason it's there, like conceptually, intuitively, there's a reason it's there. And so what I'm going to do is give you guys a couple of examples of conservative forces, and we're going to plot potential energy functions for them. The first one is a very easy one, gravity. It's one I'm most familiar with. So what I'm going to do is I'm going to plot the gravity as a function of height for a few different people. I'm going to call this a 0 point. So imagine the first guy is here. Second guy is like a little higher. A little stretched out. And this guy's a little higher. Right, now the first guy, what's his potential energy? Well, let's see, these are at different spots. So these are at different heights, okay? This guy's at 0, this guy's at a different height. And the other guy's at a different height. Now the first guy, his height is 0, his potential energy is 0. Okay, easy. The second guy's height is like some h, and his potential energy is going to be mg times that. So his height is this, his potential energy is some other number times that. The last guy, let's say, is like twice as high. His potential energy is 2 mg. So the potential energy function for gravity is very simple. It's just a linear function. It's a straight line. All this is saying is that depending on what my height is, I can tell you what the potential energy is. It's a function of the height. Now, this is saying that the force has to be the negative of the derivative of the thing. What's the slope of this graph? mg. Slope is mg. So if I take the negative derivative of mgh, I just get negative mg. Now why is it negative? The negative is there is because if you put something here, if you put some person there, which is that guy, he's at that high. Gravity wants to pull him down. The force acts downward. In other words, it looks like it's going down this graph in that direction. So the negative is there because the force, you want to make it point in a direction that makes it go down the potential energy. And that's the way things want to move in physics. We define it so that it looks like it's going down a potential energy graph because of our experience with gravity. If we defined it the other way around, it would look like it's going up a potential energy graph. Which is not wrong, but it's not as nice of a notion to think about. Because we're used to seeing things fall down. That's why we define this negative. Another example, which we may not be as familiar with, is a spring. So I'm going to do the potential energy of a spring with a relationship to how much the string is stretched out from its equilibrium point. And you can stretch it or compress it. So I'm going to put x is both positive and negative. So the first one I'm going to have is when it's like stretched out. So there's some positive delta x. The second guy I'm going to have is when it's at its equilibrium point. last one is when it's like compressed. Right? So this first guy, he has a pretty big positive x, and his potential energy is positive, so it's a positive number. This guy has 0 potential energy. This guy also has positive potential energy. The spring potential is this. So even if it's negative, when it's squared, it's a positive number. And this is a parabola because it's x squared, so it looks like this. Now that's a spring potential. Let's see if that makes sense in terms of forces. As you learned in class, I think the force of a spring is this, which is the negative derivative of that function. So let's talk about what the force is at different points in this graph. If I put it here, is a derivative positive or negative here? Derivative is positive, right? So the force has to be negative. That makes sense. If you want to go this way, I mean, he wants to compress that. Whereas if it's on this side, is the derivative positive or negative? Negative. So the force is positive, so it wants to move back. That's where the negative comes on. It makes you want to actually go down the potential energy first. Alright? When you're at 0, there's no force because the derivative is 0. When you have an equilibrium, it doesn't want to move at all. If you stretch it, it wants to go back to the center. If you compress it, it wants to go back to the center. So let's do the one. So now I want to talk about when you have it in more than one dimension, because those are the situations where we have to take partial derivatives. I'm going to give you one function. I made it a little simple so you can kind of pick it apart. This is a potential energy function, but it depends on 2 different variables. So now it's not like a particle moving in 1 dimension, it's a particle moving in 2 dimensions. And at each point it has different potential energy. So what I'm going to do is I'm going to just draw this 2 dimensions you can have the particle from. And before I draw a graph of this, I'm just going to write a bunch of numbers. Alright? And what these numbers are is when I plug in those numbers into here, what do I get? Alright, so here I'm just going to write a bunch of numbers in the graph. You don't need to really copy this down if you want to. How else? They have a lot more fun than you. A lot of fun. I like it. All right, so what I did was I plugged in all these numbers here, and I got a potential energy function that depends on both an x and y. So I plugged in x equals 0, 0, 0 to get that one. I plugged in x equals 1, and then y equals 0 to get that, etc. Now you got to visualize. If I have this plane here, those numbers represent how high the potential energy function is there. So you got to imagine the surface. Okay? So at the very beginning, at the very origin, it's still set 0, 0. If I go a little bit, in your case, if you go a little bit to like over here, now the potential energy is a little higher. Over here it's a little lower. So kind of in the middle section it's like this. And then on the sides it kind of goes up like this. So see that? Because these numbers are higher. So this potential energy function actually looks like a piece of paper like this. It's this. This is the surface that it would create, just like that. Right? So at each point, how high the surface is tells you what the potential energy is. And we have a way of visualizing what the force is in relation to potential energy. The force tells you where something would move inside its potential energy. So let's actually go and find the force. This is a good practice in derivatives. Now in partial derivatives, the force is going to be a vector because you have two different variables here. So the force is going to be negative du dx and negative du dy. And this means that you take the derivative with respect to x, the whole y constant. So this is going to give you negative 2x. And that guy's going to give you positive 1/2. The derivative with respect to y is just 1/2. But that goes to 0. I think many of you have seen partial derivatives, so if you have a question, I'll leave it here after class. I can use a question for you. I'll have it. So this is the force, okay? So what I'm going to do is just imagine a couple forces at different points. The force at, let's say the force at 0, 0. I plug in 0, 0 here. What do I get? Should be negative. 0, negative 1. Okay. Now the force at, let's say, 1, 0. That's going to be negative 2, negative 1 half. And the force at 0, 1. That's 0, negative 1 half also. So there's a couple of places. So if you imagine this, visualize this again. The 0, 0 point is right here in the center. And the force points 0, negative 1 half, which goes like this. That makes sense that it would want to go in that direction as this thing is sloped down. Now, if I'm a little bit to the right of the center, which is at 1, 0, it wants to go towards the center, and it wants to go down, which is kind of over here. So if I put something here, it's going to want to go a little bit toward the center because it's sloped that way. It also wants to go down and slope that way. So that's where these negatives are coming from. They want to go in these two different directions such that the potential energy decreases. And that's what the force is. If I draw it on here, the way to visualize this nicely is that you can just look at any one of these numbers and ask yourself, which direction is it going the fastest? That's where the force will point. So let's look at this number here. Which direction should I draw that so that you want to go down as fast as possible? With that, right? So the force points in that direction. Okay. What about this guy? Kind of the same direction, maybe? What about this one? It's going to be straight down, right? Same thing here, here. These all point in like this because you want to decrease as fast as possible. That's what this function does. It's called a gradient. The one about that you haven't yet. It tells you how something decreases or increases in the fastest possible direction. And that tells you where the force goes. When you get to 1B, this is going to be the electric field, and this is going to be the voltage. The voltage is a potential, and the field is a force. Something you'll see again. All right, so let's do one question that doesn't actually use 2 dimensions, it's using 1 dimension, so it's a little easier. Just go back to homework, and I'll stop with that. That's number 11 and number 12. Okay, so that's the potential energy function as a function of x. So what that means is if I'm over here, I have 0 potential energy. If I'm over here, I have UA potential energy. If I'm over here, I also have UA. Right? And again, we can visualize the force by looking at this graph. It just tells you the negative of the slope. So, let me draw this a little better actually. Should be really stupid, I think. So right here, if I put a particle there, first of all, is the derivative there positive or negative? Positive. So the force is negative, right? Positive in that direction. Is the derivative a big number there or small number? Yeah. The slope is really big, so that means the force is really big. That makes sense. If you have something on a really steep hill, it's going to want to go down really quickly. It's a high force. So the slope is related to the force in the thing. You want to go down really quickly. Same thing over here wants to go negative slope means it's going to go positive force. What about right here?
Equilibrium?
Yeah, there's no force. Technically, it's equilibrium. This is called unstable equilibrium. If you kind of kick it out of the direction, it's going to fall. So it's very unstable, but it's equilibrium technically. And then, et cetera, et cetera. So the first question says, if you put a particle right here, what is the acceleration of the particle? All right, so it is constant. Can somebody explain to me why it's constant?
It's linear.
I think I heard.
Linear.
It's linear, yeah. The slope is a constant number. So the force is constant. So we want to find acceleration. Whenever you want to find acceleration, this is not an energy thing. Energy has nothing to do with acceleration. It has to do with force has to do with acceleration. We're doing the second law. Let's try to find a force first. Well, we know the force is the negative derivative of the potential. And because it's linear, we can just find the slope of that. Just do rise over run, find the slope. And your acceleration is going to be whatever this derivative is divided by the mass. And the mass is given to you. It's 2 kilograms. 0.2 kilograms. Okay, so that gives you the force. And that makes sense. If it's more slope, it's going to feel a higher force, and it's going to want to go to the right. Because the slope is negative, it's negative, there's a chance of it. Okay, so that's the first question. Are there any questions on how I do that? I'm not going to do it, but that's the process. Yeah.
So the force is applied force?
Oh, okay, so yeah. So this is not an applied force. This is like a potential force. A spring has a potential that gives you a force. Same with gravity. This would be one of these delta U. It would be like that. The force of that. Are there any other questions? All right. So let's do the last problem, and I'm gonna let me just read out these to you. So it gives you some information here. It says you're going to put the particle here, and it's going to have an initial kinetic energy of 4 joules, and it's going to be moving in the right direction initially. So initial velocity is in the positive x direction. And it's going to ask you a bunch of questions. Number 12 asks you a bunch of questions related to this. The first question says its initial speed is 6.32. Well, I mean, that's just related to the initial kinetic energy. So just solve that. 1 FMV squared is kinetic energy. Solve that. You can check it. I'm not going to go through that. So part B says its total mechanical energy when it gets to x equals 7 meters is 16. Well, how would I find its total kinetic energy at some other point?
It's like the mechanical, all the energy minus the potential, you get kinetic. But the way I figure that out, it's at the bottom, there's no potential energy, it has to be all kinetic energy.
Okay, so he's saying that the kinetic has to be negative potential. What is it about the total mechanical energy that is? What is it?
It's the two
It's
ends
conserved, because there's no friction, there's no applied forces. So the point here is that this, which is the total mechanical energy, is constant, doesn't change. Everywhere it's going to be the same number. So if you know what it is at the beginning, you know what it is everywhere. Anywhere. As long as you don't start pushing it or putting any friction in it. So find out what it is at the beginning. Well, the beginning, it's going to be whatever.